Okay, so let's say we have a closed loop transfer function, such as in this block diagram right here. When we have the closed loop transfer function, then we have these formulas that we had talked about for finding the steady state error. And when you have a closed loop transfer function, as you know, it's going to look, you get this transfer function, and you have this error. Okay, so the problem that we were looking at was not a closed loop transfer function. So let's just talk about in general what we mean by error, and then how you calculate it when you don't have that. So let's say we have a question like this. Okay, so what that means is that we have our input R, and that is input is a unit step. And then we have 96 s plus 3 over s plus 8 s squared plus 8s plus 36. And we have, I didn't draw that well, make that just R. And we get Y. Okay, so that's what we have. So I'm just going to call this G. So, well, it's T. It's T, so use that. Okay, so so what is our error? So our error would be what we would have if we had this feedback right here. That was a minus, that was a plus. And the error would be what we would get right there after you take the Laplace transform. So remember, like with our balance, we were trying to keep the ping pong ball in a certain place. And so we want the difference between our input and our output to be 0. And when it is not, that is the error. So our error is going to be the difference between R and Y. So before we take the Laplace transform, this would be lowercase. So the error would be the difference between R and Y. Okay, so we want to know what this steady state error is. So that means over a long period of time, when it gets to be steady, what is that error? So that would be the limit as time goes to infinity of R minus Y. Well, by the final value theorem, that will equal the limit as s goes to 0. If we just call this E of the Laplace transform of the error function times s. So that's the final value theorem tells us that. And so the Laplace transform of R minus Y would be the limit as s goes to 0 of s of Laplace transform of R minus the Laplace transform of Y. Okay, now what is Y? Well, remember, this was not actually a closed loop, this was an open loop, and so this was just R and then T, and then we got Y, and that's not a good block diagram. Pretend it's a good block diagram. And then, so what was Y? Y was just R times T. So Y is R times T. We have the Laplace transform of T that was given. R was a unit step function, and we are given what the Laplace transform of a unit step function is. It's 1 over s. So y is r times t, which is 1 over s times r, and also we have it right here, r times t. So 96 s plus 3 s over s plus 8 times s squared plus 8s plus 36. Alright, so that's what y is. So now I want the limit as s goes to infinity of r minus y. So the limit as as s goes to 0 of s times r, which is the Laplace transform of the unit step, which is 1 over s, minus y, which we just said was 1 over s times 96 s plus 3 over s plus 8 s squared plus 8s plus 36. So now, if I multiply that s through, I get the limit as s approaches 0 of 1 minus 1 times t, so 1 minus t, or 1 minus the limit as s goes to 0 of t. And if we plug 0 in there, I don't know why we were getting a different number before, but 96 times 3 over 8 times 36, and let's see, that's 18, carry the 1, to 88 over 48, carry the 4, to 88, yeah, that's 1. So that's just 1 minus 1, and that's 0, and that's why the steady state is 0. So the reason why we couldn't use these formulas that we would like to use is we're not starting with a closed loop transfer function. We were starting with a closed loop transfer function. I apologize, we were, but we were not starting with one that had unity feedback. We were just told this is a closed loop transfer function that looks like this. What you want to have if you want to apply these formulas is a closed loop transfer system. Closed loop transfer system with unity negative feedback. Transfer system with unity negative feedback. And if you already have that, then you can apply these formulas. And if you don't already have that, then you just do what I did right here. So it's not what you would do. What you're looking for in that instance is you want to take this. So you would want to have the limit as s goes to 0 of s times the Laplace transform of r, and then minus y, and remembering that y is not the same as g. Alright, that's that.